Welcome back, everyone. This is the last section in Chapter 13 of Chemical Equilibrium. And we have a different equilibrium situation today, and this is basically when a salt is dissolved in water, it breaks apart into ions. And once it's saturated, if it's saturated, there's no more ions that can break apart because there's no more water available to break it apart. So at saturation, if you have saturation, you now have an equilibrium between the solid and the amount of ions that it breaks apart into. So we have different solubility. Now you remember when we did the swimming pool that some salts are soluble, okay, and some salts are insoluble. Now that's a little bit too easy of an answer. Some salts dissolve and some salts don't dissolve. They dissolve, all of them dissolve somewhat. There's a little bit of solubility. But if you have a very slightly soluble salt, they can differ in the amount of solubility. Some can be very insoluble, where almost nothing dissolves, and others can be slightly more soluble. So we're going to look at the last of these K values in this chapter, and that is the solubility product. So it's a constant, and if you remember, a constant is simply a number that shows a relationship. It shows the relationship between the amount of solid that you have at a saturated solution and the amount of dissolved ions that you have in a solution. So to remind you of the saturated solution, all the solvent is busy solvating or surrounding the different ions that has been broken apart. Okay, if you ever add any more solute after it's saturated, you end up with solute that just sinks to the bottom of the test tube. Okay, so since every bit of the water is occupied and no more solute will dissolve, you've got a relationship. It's an equilibrium. So the rate of dissolving is going to be equal to the rate of recrystallization. Okay, so you remember this is getting off the bus, getting on the bus. Once it dissolves, some of those ions are bumping into each other, and when they bump into each other, they're going to form a crystal. Okay, but at that same rate that solid breaks apart, the ions are going to recrystallize back into a solid. Okay, so once it's at equilibrium, the amounts don't change. So you say so many grams of this salt dissolves in 1 milliliter of water. Okay, and that's the amount, and it doesn't change once it's at equilibrium. Okay, but we're going to see that there is a relationship between the amount that is solid and the amount that is in ions, and that is what is going to be expressed by this K sub Sp, which is the solubility product expression. Okay, so let's look at it. This is very similar to the K sub C. Remember, the K sub C told you whether or not it's likely to have more product made or more reactant that's left as reactant. Okay, so this is going to tell you, is it likely that you're going to get lots and lots of ions, which means is it soluble, or is it likely that you're going to get lots and lots of solid, which means is it insoluble? Okay, so this is how that swimming pool was actually put together. Lots and lots of salts were dissolved, and some SP values were determined, and then they were ranked in terms of solubility. How much soluble is it, or how unsoluble is it? Okay, so and that's a too simplistic of an answer in reality, but for now this is totally okay for what we're going to be doing. So it gives the concentrations at constant temperature, and it's expressed as K sub Sp. Now, do you remember that when we did the K sub C value, only gases were looked at. We didn't look at solids. Solids were just ignored. Liquids, pure substances were ignored. Okay. In this situation, any pure compound that's not broken apart into ions is ignored. We're only looking at the amount of ions produced, and so our K sub Sp value is only going to be the concentration of ions made. Okay, so Also, I want to remind you of the peanut butter sandwich. If you have 1 mole of peanut butter sandwiches, then, and there's 2 pieces of bread in it, then you're going to have 1 mole of each. Okay, so you'll have 1 mole of left side bread and 1 mole of right side bread. So if you have a compound that breaks apart into 2 ions, a cation and an anion, and you have 1 mole of salt, when it breaks apart, you're going to have 2 moles total, but 1 mole of the positive and 1 mole of the negative. So you can actually determine the amount based upon the solubility given that you'll see. Okay, so let's look at this. If you have iron hydroxide, it's going to dissociate into iron 2 plus. Okay, because remember hydroxide is -1. There's 2 -1s, so this must be iron 2. So iron 2 is iron 2 plus, and 2 hydroxides, 2 OH minuses. So now I've got a coefficient. Remember, every K value is going to be the concentrations of the products taken to the power of their coefficient divided by whatever the reactants are. Now, we don't have any, the reactants here is solid, and we're going to ignore that. A pure solid liquid, we're not going to bother, it won't bother us. We're only looking here at the aqueous dissolved ions. Okay, so look to the right. This is the products. I've got Fe2 plus and 2 OH minus. So when I find the K sub Sp value of this, I'm going to have the concentration of the iron 2 ion, and then the concentration of the hydroxide raised to the second power, since there was a coefficient there of 2. So here is your guide. You're going to write the equilibrium equation and then the solubility product expression that we just did, and substitute the molar values that you're given in the problem. Here's an example. Calculate the K sub Sp of lead sulfate when its solubility is 1.4 times 10 to the -4 molar. Now remember, sulfate is the yellow lady. Lead is one of the 6 exceptions. So when we learned this, we learned that it was insoluble, okay, an insoluble salt. But insoluble is relative. It's how soluble is it? It's not just yes or no. There's degrees of it breaking apart into ions or not. Okay, so this one has a solubility of 1.4 times 10 to the -4 molar. That means in every liter of water, you are going to get 0.0014 moles of lead sulfate dissolve in a liter. A liter is like half of a 2 liter. Okay, that's a lot of water and a tiny, tiny, tiny little bit of grams of salt. Tiny little amount. Okay, so it's very, very insoluble. It's slightly soluble if you want to think about that. So first of all, we need the expression. If you remember the expression, you're going to break it up into its ions. So you put lead sulfate on the left, and then you're going to break it apart. Now it's in equilibrium. That's what the double arrow means. So some of it is recrystallizing into the solid, some is breaking or dissociating back into the ions. So you have lead S2 and sulfate 2. Now, when you break this lead sulfate up, this is -2, and it's matching with lead, so this has to be lead 2. Remember, there's 2 options. There's lead 2 and lead 3. So since this, this is -2, this has to be +2. So it's just going to break up to 2 to 2. So this is a 1-to-1. This is 2 pieces of bread in the peanut butter sandwich. That means if I have 1.4 moles, 1.4 times 10 to the -4 moles per liter, that means when it breaks apart, I'm going to have 1.4 times 10 to the -4 moles of this side of the bread, and 1.4 times 10 to the -4 moles of this side of the bread. Okay, so when I do the K sub Sp, remember it's going to be the concentration of the lead 2 plus, and there's no coefficient, so it's taken to the 1 power, times the concentration of S2O4 to the -2, and it's taken to the 1 power since there's no coefficient here. And so what is it? This is, remember, if the solubility is 1 mole of lead sulfate per liter, and that's a peanut butter sandwich, and it breaks apart into equal sides, the same, so there's nothing taken to the powers, That means that's one piece of bread. It's 1.4 times 10 to the negative 4 left pieces and 1.4 times 10 to the negative 4 right pieces. So this is going to be the k sub sp of this and the k sub sp of this. Okay, so it's going to be the concentration of the lead times the concentration of the sulfate. So we substitute that in. And remember, this is a solid, so we're going to ignore it. There's nothing on the bottom. It's just divided by 1. And so when you multiply this 2, the k sub sp is 2 times 10 to the negative 8. Now that's a very small number. Very small number. That means the amount of ions in the water is very, very small, which implies that what's actually sitting in the water is mostly the solid. Okay. So here's solubility of some various ionic compounds. Most of these we learned as insoluble. Chlorine was in the pool. Silver was one of the exceptions. So its Sp for the whole thing is 1.8 times 10 to the negative 10. Very, very insoluble. Silver sulfate. Sulfate, remember, is the yellow lady, but silver was one of the 6 exceptions. It's 1.2 times 10 to the negative 5. Compared to each other, this is more soluble than this. But they're still so little that you can conceivably think of them as insoluble. Carbonate, remember, is the coal car on the top of the pool. So barium sulfate is very, very insoluble. The K sub Sp is very low. Barium sulfate, remember, barium is another one of the exceptions on the bottom of the pool. Very, very low, just as low as silver chloride. Calcium fluoride. Remember, I had that red flag about the fluorine. Fluorine is an insoluble, even though it's in group 7, it's insoluble. Okay. Hydroxide is high and dry, so it's insoluble. It's slightly more soluble than the silver. Calcium, remember, is one of the 6 exceptions to sulfate. Lead chloride. Lead is one of the exceptions of group 7. And lead carbonate, remember, carbonates are insoluble. Okay. The molar solubility is the number of moles of solute that dissolves in 1 liter of solution, and it's calculated from the K sub Sp. All right, and I'll show you how to do that. You write the equilibrium constant and then the solubility expression, and then you substitute exactly like we did before. You find the K sub Sp, and now from the K sub Sp, we can determine the molar solubility. I'll show you how to do it. Determine the molar solubility of strontium carbonate. Remember, carbonate is a coal car, so it's very insoluble. This is K sub Sp is 5.4 times 10 to the negative 10. So it's from the K sub Sp that we're going to determine the molar solubility. Break it apart first. Okay, you see this is negative 2, so this has to be positive 2. So it's a 1-to-1. So there's no coefficient, so this is to the 1 power, 1 to the power. So we've got the K sub Sp is the concentration of strontium, concentration of carbonate. Now look at this. This is 1-to-1. This is peanut butter sandwich again, which means if the whole thing is 5.4 times 10 to the 10, then the left side of the bread has the same concentration, and so does the right side. So both of these sides are going to use the same as this. Okay, so if there's 10 sandwiches, there's 10 left pieces of bread and there's 10 right pieces of bread. That's the idea. Okay, now you're going to substitute. If the K sub Sp is the concentration of strontium times the concentration of carbonate, you put them together. Since they're the same, you can say it's 5.4 times 10 to the negative 10 squared. Okay, right? So that's the 5 times 4 times 10 to the negative squared. Now, to solve for moles, this is moles per liter. This is moles per liter. So I've got moles squared. Okay, moles squared. So if I want to find its molarity, which is moles over liter, I need to take the square root of this number, which is the square root of 5.4 times 10 to the negative 10. And do you see it? This is the concentration of this, the molarity of this. Remember that in the brackets, that's molarity. And if I'm trying to find molarity, all I do is solve for in this case, X. They've got it as S, but X, right? The molarity of this times molarity of this. Since these are the same, it's S squared or X squared. So you take you're gonna say this is, you don't square this because this is the case of SP. That's what was given. So S squared times this is, you take the square root of it, which is 2.3 times 10 to the negative 5. Okay, that is the molarity of the molar solubility. How many moles will dissolve in a liter? Okay, the molar solubility. Okay, I think this is probably the hardest section of this chapter. So just see me in class and I'll try to help you.